Good afternoon, everybody. So this afternoon we'll have one lecture, and then we'll have a little discussion and introduction about the hands-on sessions that we'll have the other afternoons after the afternoon lecture. And so this afternoon we're starting by welcoming Simona Bordoni, who is a professor at the University of Trento in northern Italy, and who is going to talk to us about the general circulation of the atmosphere, with a particular focus on the tropical circulation. Thank you.
Great. Good afternoon, everybody. It's really a great pleasure to be here today. I'm really sorry I missed this morning's talks, but I got in at 6 a.m., so I needed some sleep. So today I was tasked to talk about the large scale, the general circulation of the atmosphere with a focus on the Hadley cell. I do know that even if I wasn't here, I had a spy in the room, and I know that you already heard a little bit about the Hadley circulation. We'll try to get a little bit more into the details of models that have been developed to understand the Hadley circulation. Here, we're interested in moist dynamics of monsoons, and so of course, I really want to start by showing the distribution of the precipitation with a focus on the tropics. This is the annual mean over the Earth's surface from GPCP. Because we really, of course, we are interested, at least here as part of this workshop, on the large-scale circulation, atmospheric circulation, its interaction with moist convection and precipitation. So I think that we're all familiar with these patterns. We clearly see that precipitation is, in the tropics, is primarily organized, especially over the oceans, along bands that are narrow in latitudes but extended in longitudes. That's what we refer to as Inter-Tropical Convergence Zones. We clearly, of course, see also significant precipitation over the tropical and subtropical land masses, but there, especially as you move away from the deep tropics, that is really the imprint of on the annual mean precipitation of a strong seasonality of precipitation associated with monsoons. Outside of the tropics, we see tilted rainfall bands that we usually call storm tracks. This is where extratropical storms tend to form and dump a lot of precipitation. If now, for each latitude, we take a zonal average, we obtain this zonally averaged distribution of precipitation from the equator moving towards both poles, and we see the familiar pattern of alternating wetter and drier bands, with the wettest bands being close to the equator, dry zones in the subtropics, and two broader wetter bands in the extratropics of both hemispheres. One interesting aspect of this distribution is that maximum precipitation is not located at the equator. In fact, is located north of the equator at around 6 degrees north of the equator in present-day climate, nor do we see that this distribution is symmetric about the equator. Definitely, precipitation prefers the northern hemisphere. And so this, of course, points to an asymmetry between the two hemispheres that makes the northern hemisphere more favorable for precipitation. And what is the most relevant asymmetry is something that has been discussed at length in the literature. And let me emphasize how consensus in the literature has emerged only in the past 10 years or so. And the primary reason is now believed to be not, for instance, the asymmetry in the distribution of the land masses that are more, of course, cover larger fractional areas in the northern hemisphere, but is associated with the ocean circulation, especially in the Atlantic, that transports energy from the southern to the northern hemisphere. And if there is interest, I won't be talking about this, but if there is any interest, of course, we can discuss it during breaks. Of course, these patterns, at least in terms of the zonal mean of the zonally average precipitation, are clearly have a strong tie with the overturning circulation in the meridional plane, characterized by two Hadley circulations that are about more or less symmetric, or I should say anti-symmetric, about the equator, although we clearly see that the northward displaced position of the ITCZ coincides or is accompanied by the fact that the poleward boundary between the southern and the northern cell is displaced north of the equator. And so maximum precipitation tends to be collocated with the ascending branch of the Hadley cell, and the dry zones are under the influence of the descending motions in the descending branches of the Hadley cell. We will see how this is what we usually refer to as a thermally direct cell, warmer air going up, colder air coming down, but we will see that is also an energetically direct cell in a way that I'll explain in a minute. Outside of the tropics, we find the Ferrel cells. Those are indirect cells, and if there is time, I'm not sure I'll have time, I'll talk a little bit at what maintains these Ferrel cells outside of the tropics. It's also important to notice how the latitudes that are in which the Hadley cells exist are also latitudes in which the surface winds are easterlies. So in general, the existence of a general circulation of the atmosphere is explained as coming out of a constraint from the radiative energy budget at the top of the atmosphere, which I'm sure you've all seen previously. Shown here, the red curve shows the distribution as a function of latitude of the net shortwave radiation absorbed, that is absorbed by the climate system, and the blue curve represents the outgoing long-wave radiation. And we clearly see that latitude by latitude, our system is not in radiative equilibrium in the sense that there are regions, and in particular in the tropics, we see that there is net energy surplus. There is more energy that is absorbed than the one that is emitted back to space, whereas outside of the tropics, here broadly defined in general, is 45 to south to 40 degrees north, where we have this region of net energy surplus. Outside of this region, we have a net energy deficit. This is to say, here we have more energy that is lost as OLR emitted back to space than the one that is absorbed. And of course, for the system to reach steady state and equilibrium, then there needs to be a general circulation of the atmosphere and the ocean. Both of the fluids in the climate system accomplish this, that need to transport energy from the regions of net energy surplus to the regions of net energy deficit. And so this is what the black curve here shows. It's the implied energy transport, the transport that is implied by this observed radiative energy budget. And negative means southward, positive means northward. So we see that in both hemispheres, the implied energy transport is directed poleward in both hemispheres. And then we can decompose this total transport by the one that is accomplished by the ocean, the blue dotted curve, and the one that is accomplished by the atmosphere, which is the dashed or dotted dashed red curve. So we see that most of the transport in the deeper tropics is affected by the ocean, but then at higher latitudes, it's really the atmosphere that is doing this job. And in the tropics, it's really the overturning circulation. It's really the Hadley cell that is accomplished the required poleward energy transport. And this here, we can actually look at how and why the Hadley cell is in fact an energetically direct cell, in the sense that the relevant energy that is transported by the Hadley circulation is the moist static energy, whose typical vertical profile in the tropics is shown here. So moist static energy, I don't know if it was introduced early this morning, is an important quantity for many reasons. It's for instance, one of the moist conserved quantities from a moist parcel perspective is also the energy that is transported by the general circulation of the atmosphere, and it comprises dry enthalpy, potential energy GZ, and the latent energy associated with moisture. And because the moist static energy values in the upper branch of the Hadley cell tend to be larger than those at the surface, when you vertically integrate the transport of moist static energy by the Hadley circulation, you actually see that this is on average forward. And in particular, moist static energy is transported in the direction of the upper level flow. So the Hadley cell is transporting sensible and latent energy towards its ascending branch, but it's transporting moist static energy away from its ascending branch. And so it's really accomplishing this poleward energy transport that is required by the energy budget. But here, I really want to ask the question, could a state of radiating equilibrium be a plausible state for our atmosphere? And I know that I think the first lecture this morning, or maybe the second, introduced radiative and radiative convective equilibrium. We'll go quickly here. But then the first question is, could radiative or radiative convective equilibrium be a plausible state for our atmosphere? And so let's start by considering the thermodynamic equation. This is just the first law of thermodynamics. And let's consider a situation where there is no motion whatsoever, nor horizontal nor vertical motion. So of course, this means that both the horizontal advection and this term that is proportional to the vertical velocity are equal to 0. So now the thermodynamic equation becomes a balance between energy that is stored in the atmosphere and any diabatic heating or cooling, which without any motion can only be through radiation. And so in steady state, then the thermodynamic equation just reduces to a statement that level by level, there cannot be any net radiative heating or cooling. And if you express it in terms of the divergence of the radiative flux, we cannot have any vertical divergence or convergence of the radiative fluxes. So this is the radiative equilibrium equation. And notice how it only depends on the vertical coordinate. And so we can solve for radiative equilibrium independently for each atmospheric column. And so with a suitable radiative transfer code, one can solve for the temperature profile that would exist at radiative equilibrium. For instance, by providing the solar radiation flux at the top of the atmosphere and the distribution of the radiatively active gases, for instance, including water vapor and clouds. And Madhava and Strickler in 1964 were the first ones to perform such calculations. And I think you saw this plot, and this is just a readaptation of the original plot shown in Madhava and Strickler in 1964 with the purple curve representing the pure radiative equilibrium calculations. And there is a few unrealistic features of this solution. First of all, notice how there is a big jump or a discontinuity in temperature between the surface temperature, which is much warmer than the observed one, and that of the atmospheric level just above the surface. And this primarily arises because if you let exchanges of energy only occur through radiative fluxes, most of the incoming solar radiation is absorbed at the surface, and so this creates this jump. Then you see that the temperature lapse rate is very steep, and in particular, especially in the lower troposphere, the tropopause temperature is too cold and the tropopause height is too low. And in particular, and I think this was discussed this morning, you see that the radiative temperature profile is convectively unstable. So radiative equilibrium would lead to convection, and hence the atmosphere would no longer be stationary. And so convective instability implies vertical motion on small convective spatial scales that develops within each column to remove the instability. And here we're going to assume that this doesn't drive any large-scale circulation. And the state that you get is radiative convective equilibrium. In radiative convective equilibrium, you have a balance now between the net radiative cooling and the net convective heating within each column. And so here, the important thing is that there is a separation between the typical timescales associated with convection, which is a very fast process, compared to radiative process. And so convection, once it develops, we expect it to remove rapidly the instability that is produced by the slower radiative processes, and convection will keep the temperature lapse rate close to a condition of convective neutrality. What is that state of convective neutrality depends on whether you're assuming you're a dry or a moist atmosphere. And in the calculation by Strickler, Madhava and Strickler, this was enforced as a hard adjustment. Basically, as soon as radiation would produce instability, you relax the lapse rate to a prescribed lapse rate. And again, they performed a couple of additional calculations. The red curve here represents the simulation where you impose dry convective neutrality, so where the lapse rate is kept as a dry adiabatic value, whereas the green is the calculation that in fact was performed by Madhava and Strickler that basically assumed that they relax the temperature lapse rate to an typical observed value of about 6.5 Kelvin per kilometer. And this plot, which is taken from Hartmann, Global Physical Climatology, a textbook that you might be familiar with, they also performed this calculation by using an actual moist adiabatic. And you see that there is very little difference between the moist adiabatic condition and the relaxation to a global average. And again, here, the important point that I want you to notice is that now, even in this very simple calculation, again, this was performed in 1964, you get a temperature profile, and this you can interpret it as being typical of a tropical atmosphere, a global average, depending exactly you specify some aspects of these calculations. But now you find that, first of all, you get rid of this artificial jump between the surface temperature and the atmospheric temperature. You get values that are much closer to the observations, both in terms of the surface temperature, the lapse rate, the position, and the temperature, the height and the temperature of the tropopause. So then the question is, can this RCE be a plausible state? In fact, RCE is often used as a theoretical paradigm to understand many aspects of the tropical circulation. So can the state be achieved? We already know that, of course not. That was our answer, right? We don't have a distribution of the top of atmosphere radiative fluxes that tell us that our atmosphere is in radiative equilibrium, in which latitude by latitude, the absorbed solar radiation coincides with the emitted outgoing long-wave radiation. So why is that the case? So why don't we have a state of radiative convective equilibrium? And so, as we said above, RCE describes a state in which the thermodynamic balance within each column is a balance between radiative cooling and convective heating. And under certain simplifying assumptions, we can use radiative convective equilibrium to construct a complete solution to the governing equations. And so again, here we're going to assume the following. The local thermodynamic balance is that of radiative convective equilibrium. Each column is in hydrostatic balance. There is no large-scale meridional overturning circulation. This means that there is no vertical and no meridional motion. We will see that there is zonal wind, but there is no meridional, no vertical motion. The solution is axisymmetric, so all quantities are independent of longitude, and the winds at the surface are identically equal to 0. I hope that I don't need to show the thermodynamic equation again. We know how this is verified. And I'll show you the primitive equations in log pressure coordinates. I don't know if you've ever met in your life log pressure coordinates. If you haven't, don't worry. I have a slide if you're interested in the actual definition, but basically a variant of pressure coordinates. The advantage of pressure coordinates is that, for instance, geostrophic relations simplify, and the continuity equation basically reduces to a statement of divergentless flow. And when you use the log pressure coordinates a little bit, you need to put in this condition for non-divergent flow. You need to include in the vertical component the density, but again, at the end, it's still a much simpler diagnostic statement of mass conservation. So this is the zonal, this is the meridional, and this is the vertical momentum equation under the assumption of hydrostatic balance, okay? So what would this state of RCE correspond to hydrostatic balance in the vertical direction? If you think about steady state and no meridional and vertical motion, basically you get a trivial balance, and also we assumed that there is no, all the fields do not depend on longitude, so the zonal momentum balance is trivially verified, 0 is equal to 0, but then there is the meridional momentum equation. So what does the meridional momentum equation imply? This is a more general expression of thermal wind balance. It's basically a statement that you get where zonal winds that are in balance with the meridional geopotential gradient. And you also have the metric term, so we refer to this balance gradient wind balance. We can now go back to the hydrostatic balance, integrate in the vertical direction. You get something that, if you're familiar with it, looks very much like the hypsometric equation. Here we're gonna neglect the contribution of the geopotential at the surface. Basically this is equivalent to assuming surface winds exactly equal to 0. And so we get a statement that the geopotential at any given height, Z star is our vertical coordinate, it's basically proportional to the average temperature in the layer. Again, this is simply a statement that a layer that is warmer is thicker in height. Okay, so now if we replace in the meridional momentum equation, we now see that, again, there is a zonal wind in the meridional direction that is proportional to any meridional gradient in the temperature. So this is to say that while in RCE we do not have any meridional nor vertical motion, so we don't have any communication between the different columns as a function of latitude. There is a zonal wind that is in gradient wind balance with the meridional temperature gradient. And so let me here summarize again what are the properties of this RCE solution that we just derived. The RCE solution has no large scale overturning. The solar energy absorbed at each latitude is re-emitted, is balanced by OLR, re-emitted back to space as longer radiation. There is no energy transport in the meridional direction. We only have convection that is transporting energy in the vertical direction. And so why doesn't the Earth general circulation look like this state of RCE? And of course, there are a number of possible answers. Some of those are, for instance, the fact that we have neglected the seasonal cycle. We have assumed that convection remains local. Convection might not remain local and might be driving larger scale circulations. Of course, we are considering an axisymmetric planet, no variations with longitude. So all of this might be plausible reasons, but in reality, there is one fundamental reason for which RCE is not realized, and this arises from another fundamental balance that constrains the general circulation of the atmosphere. It's not just the energy budget, but it's also the angular momentum budget, which I think was hinted at or partly described in the earlier lecture before class. So what do we mean by angular momentum here? We're thinking about the angular momentum about the Earth's spin axis, which has a planetary component and a relative component. And here already made the thin shell approximation. And basically what this means is that if you're considering an air parcel at any given height z from the surface, we're just considering that equal to 0. What really matters is the radius of our planet, because the atmosphere and the ocean, for that matter as well, represent thin shells around our planet. And so the constraint that arises and applies to an axisymmetric atmosphere that makes the RCE an implausible state for our atmosphere. So this constraint takes the name of the Heights theorem. I don't have time to go through all of the details of the Heights theorem, but here the important thing is that the Heights theorem applies to an axisymmetric atmosphere. Again, we are neglecting variations with longitude in which angular momentum disperses diffusively. And one can show that if this is true, angular momentum anywhere in the interior atmosphere cannot exceed the planetary angular momentum value at the equator. That is to say, no matter where you are in your atmosphere, and this means what is your latitude, and this is the total angular momentum, this value cannot exceed that of the planetary angular momentum computed at the equator. If we go back, the angular momentum computed at the equator is just omega a squared. Okay, so now we can turn this into a constraint on the zonal winds that can be attained anywhere in an axisymmetric atmosphere. And this is what we get. We get that anywhere in this axisymmetric atmosphere, the zonal winds need to be smaller or equal to the angular momentum conserving winds that are proportional to the sine squared of latitude, inversely proportional to the cosine of latitude. And I'm sure that you have seen this angular momentum conserving winds again in the lecture before. I think there was also some estimates of how big it would get if, again, angular momentum is strictly conserved. And you can think of this as being the angular momentum of an air parcel that rises from the equator and moves poleward starting from 0 surface winds. And notice how this distribution is symmetric about the equator because it depends on the sign of latitude. You develop westerlies in both hemispheres as you start moving away from the equator. And so, again, this is the important constraint. The zonal winds need to be everywhere smaller than or at most equal to the angular momentum conserving winds. And in particular, at the equator, the angular momentum conserving winds are 0. And so you cannot have westerly winds at the equator. When that happens, we talk about equatorial superrotation, and there are planets that do have equatorial superrotation, and that implies that of course this condition, that angular momentum disperses diffusively, which means down the angular momentum gradient, is no longer verified. For instance, you can have waves in these planetary atmospheres that converge angular momentum into the equatorial region. And in fact, this happens in our atmosphere as well, but this convergence is not large enough to cancel, in fact, the angular momentum transport by the Hadley circulation. Okay, so I hope that you are seeing where we're going. So we are trying to understand why the RCE state is not a plausible state. We obtain a constraint on the attainable zonal winds, and because the basically gradient wind balance establishes this relationship between the zonal winds and the meridional temperature gradients, we can recast this condition on the zonal winds on a condition on the meridional temperature gradients that can be obtained so to satisfy this angular momentum budget constraint, the Hyde's theorem. And I did this already for you. Again, if you're interested and you don't see how this calculation has been done, let me know. We can go through this together. But basically, you find that the meridional geopotential gradient that are directly proportional to the meridional temperature gradient need to be smaller or equal than this value. Notice this cubic dependence on the latitude. That is to say, and again, these I already made the small angle approximation because we are close to the tropics. And so what this means is that the geopotential and the temperature cannot decrease more rapidly than with the fourth power of latitude, okay? So the constraint on zonal winds implies a strong constraint on the geopotential or the temperature, the average temperature, which cannot decrease more rapidly than quartically with latitude. And here I plotted what this behavior, of course this is normalized of the geopotential, would be as a function of latitude. Let's zoom close to the equator in the tropics because that's what we are interested in. This is your quartic dependence, the fourth power of temperature. That is the one that is the largest variation, largest decline attainable if you have third, second, 1 power of the of latitude of the geopotential. Your decrease with latitude of the geopotential and the temperature would be too fast. You would get winds that in gradient wind balance with this geopotential would be too strong and would basically not satisfy the Hyde's theorem. And so if then the question, okay, so we now know what variations of the temperature, the geopotential with latitude need to be so that this fundamental constraint is verified. And so the question is, does RCE verify the Hyde's theorem or not? Because if it does, then the RCE state would be perfectly plausible. And so for the Earth's atmosphere, it turns out that the latitude dependence of the vertically average temperature, again, you would get those, you would get that profile of temperature simply so that because the OLR is dependent on temperature, it would match latitude by latitude the distribution of the solar insolation, and basically that distribution would depend on the sine square of latitude. That is, if you make the small angle approximation, again, sorry, here I'm going a bit fast, but here we're just saying that the radiative equilibrium would be equal to the value at the equator minus this delta H that represents the pole to equator temperature difference multiplied by the sine square of theta. And if you make the small angle approximation, this is just equal to theta squared. This is too rapid of a decline. And so the Hyde's theorem for the RCE state is not verified. And in particular, you can show that in fact, RCE implies westerly winds at the equator. This is not attainable. And so that is why a Hadley cell needs to exist. And it needs to exist so that it distributes energy, so that you get temperature gradients that are at least as weak as what is constrained by the Hyde's theorem, if not weaker, so that again, the resulting zonal wind satisfies the Hyde's theorem. And in fact, I'm not gonna do it because I'm a little bit constrained with time. I don't even know how I'm doing with time here, but you can show that Again, you can do this very simple calculations, and you can show that you can actually come up with a simple estimate of the extent of the Hadley circulation just by looking at the range of latitudes within which the RCE state has zonal winds that are larger than the angular momentum conserving winds. Outside of this latitude range, the RCE can exist, no problem, or at least it does not violate the Heights theorem. Then things get more complicated because in reality then the temperature gradient that sustains the zonal winds outside of the tropics becomes baroclinically unstable, and so then you have formation of baroclinic eddies that also forces the extratropical atmosphere to deviate from RCE. But in fact, the very simple theories of Hadley cells that were based on axisymmetric models just assume the existence of a Hadley circulation within the tropics with the atmosphere just outside of the tropics being in RCE. Okay? Any questions about this so far? Okay, so then we are going to move on, and we're gonna be looking at a classic solution of the Hadley circulation, the so-called Held and Howe model. And this model to these days remains somewhat of a classic theory for the Hadley circulation because you can actually derive a complete and analytical solution for important aspects of the Hadley circulation, such as, for instance, the strength and the extent of the Hadley circulation. And so the assumptions that we're gonna make is that above the boundary layer, although in this model there is really no boundary layer, just surface friction, above the boundary layer, the atmosphere is nearly inviscid. And what this means, nearly in this, is that there is some viscosity, but the viscosity is small. So there is some viscosity, which means angular momentum diffuses down the gradient so that the Heights theorem still applies, which means we know that if the Heights theorem applies, the RC state within the tropical bands is not satisfied and we need a Hadley circulation. But we also are going to assume that viscosity is small enough that in the upper troposphere, the winds are exactly the ones that satisfy conservation of angular momentum. So in this solution, you are giving yourself already the zonal winds. You know what the zonal winds are. Again, you make the assumption that basically zonal, the angular momentum that is conserved, is the one of an air parcel that starts from the surface at the equator with 0 relative velocity. And so the angular momentum that is conserved is the planetary angular momentum at the equator. And as we saw already, this distribution as a function of latitude is omega, rotation rate, a, the sine square of latitude divided by the cosine of latitude. We are going to assume that there is a Hadley cell in the tropics up to a certain latitude, and this is one of our unknowns in the problem. We're gonna call this theta HC, theta Hadley cell. And as we said, poleward of this latitude, because RCE is a plausible state, we're gonna assume that the atmosphere is in the RCE state. We're also gonna make the assumption that the Hadley cell is energetically closed. And what this means is that the Hadley cell only redistributes energy in the meridional direction. We will see that basically what this means is that regions of net, the overall integral of the net cooling needs to be equal to the integral of the net warming in the ascending and descending branch of the Hadley cell respectively. Then we are also going to require that the temperatures are continuous at the Hadley cell edge. Again, within the Hadley cell, we're gonna call T sub m the temperatures that are in gradient wind balance with the zonal winds that are angular momentum conserving. So everything with the m refers to the distribution of the temperatures and the zonal winds within the Hadley cell. And those are constrained by angular momentum conservation. Outside of the Hadley cell, we said that the state is one in which the atmosphere is super happy to be in radiative convective equilibrium, and we call this temperature T sub E. Those are the radiative convective equilibrium temperature. And continuity at the Hadley cell's edge implies that at the cell's edge, these two values need to be the same. The model is completely axisymmetric. There are no variations in longitude, including large-scale eddies. It is also a dry model. And then, as I said before, we're going to assume that the temperature in radiative convective equilibrium basically decreases away from an equatorial value with the squared of latitude. Okay, so let me here emphasize this important point, because we are assuming that we know what the angular momentum conserving winds are. I'm sorry, what the zonal winds are, which we're saying are the angular momentum conserving winds. We can integrate in the meridional direction gradient wind balance, and you make the small angle approximation, because if now you replace here, you just assume that your winds are the angular momentum conserving winds, you exactly know what these are. And so now you exactly know what is the meridional gradient of your temperature. And it turns out that temperature needs to decrease quartically with latitude. This is the most rapid behavior. Sorry, I am going in the wrong direction. Is this, oh, I thought I had the, I cannot. I had this plot of the, oh, here, sorry. So basically, what we are assuming when you use the constraint of conservation of angular momentum, your geopotential and your temperature decrease with the fourth power of latitude. So you know that shape. What you do not know is the value that temperature takes at the equator, okay? And so that is exactly what I wrote here. Oh, here there is a theta to the fourth that I forgot. There is the latitudinal dependence, which is again with latitude to the fourth power. And again, this is just to say that when you assume that angular momentum is conserved, your temperature within the Hadley cell decreases from a value at the equator, which is an unknown value, which we need to solve for, with, again, the fourth power of latitude. There is a theta 4 here missing. And so in this problem now, we have two unknowns. One is the extent of the Hadley circulation. The other is the value of the temperature at the equator. Those are the two unknowns that we need to solve for. And to do this, we need two equations, two unknowns. We need two equations. And we basically just use conservation of energy within the Hadley cell. And here, basically, what you just need to impose is that the difference between the radiative equilibrium temperature and the actual temperature within the Hadley cell integrated over the latitude span of the Hadley cell is equal to 0. And then you also impose continuity of temperature at the Hadley cell's edge. And what you find is this form of this estimate for the extent of the Hadley cell. Oh, sorry, there is a few mistakes here. There is a 1/3 power here that I forgot. I'll correct the slides, and I will send them to you. And here also, we are just estimating the extent of the Hadley circulation at the top, at the tropopause height. And basically, if you plug in any reasonable estimate for all of these parameters, for instance, the pole to equator temperature gradient and the surface temperature, one really of the great successes of this theory is the fact that it predicts an extent of the Hadley circulation that is very similar to the one that we observed. One caveat here to keep in mind is that this pole to equator temperature gradient is not actually the observed temperature gradient, in the sense that, of course, the observed temperature gradient is influenced by, of course, what the general circulation of the atmosphere is doing. So this distribution of energy, this flattening of the temperature gradients, but is the pole to equator temperature gradient that you would have if your system were in radiative convective equilibrium, okay? So this is a stronger, larger temperature gradient than the observed one, because of course the observed one is already taking into account is influenced by the transport of energy by the Hadley circulation. So this is the analytical theory, but in reality, the interpretation is very, very simple. And this is where I want to show you what the graphical interpretation is really telling us. So this is and this is taken from Heldenhauer 1980. Actually, it's a revised version by Wallace. But basically, the dash curve here represents the temperature that you would get in radiative convective equilibrium. It's this sine square of latitude, where we know the value at the equator, we know the pole to equator temperature gradient. Because we enforce the constraint that angular momentum is conserved, we said that we know the shape of the actual temperatures within the Hadley cell that are in gradient wind balance with the angular momentum conserving winds. We know the shape, but we don't know the value at the equator. Where the two curves intersect, this is your edge of the Hadley circulation. This is the condition of continuity of temperature. And so by imposing the additional constraint that the Hadley cell is only redistributing energy and energy is conserved within the Hadley cell, basically you are adjusting this curve. You're moving it up or down so that the area of net warming, which is where the radiative equilibrium temperatures are larger than the actual temperatures, and the area in the region of cooling where your actual temperatures are larger than the equilibrium temperature are the same. And this is what we call the equal area construction. Again, just by you find basically the value of the actual temperatures at the equator, which also gives you an estimate for the extent of the Hadley cell based on this equal area construction, where these two areas are the same. Okay? And let me emphasize how, despite its simplifications and limitations, one of the most important aspects of this model is that it predicts a finite extent of the Hadley circulation, even in a purely axisymmetric atmosphere, even without saying anything about the extratropics, and in particular the fact that, of course, we all know that the extratropical atmosphere is for sure not axisymmetric, even in the absence of large-scale eddies, including baroclinic eddies that develop in the extratropics. This theory predicts the finite extent of the Hadley circulation. So we emphasized, of course, the good things, the things that this theory is able to capture well. So as we said, this gives us a good agreement with observations for the extent, but the strength, it grossly underestimates the strength of the Hadley circulation by a factor of about 2 orders of magnitude. And another unrealistic feature is this continuity of winds at the cell's edge. As we said, we require that the temperatures are continuous at the cell's edge, but this condition implies in this continuity on the winds. This is the distribution, the flat, this constant line is the distribution of the winds that you would get in radiative, the zonal winds that you would get in radiative convective equilibrium. This is your angular momentum conserving winds that depend on basically theta squared. And you see that at the Hadley cell's edge, the angular momentum conserving, so the winds of our solution, are larger than the zonal winds in radiative convective equilibrium. And so when you basically transition, this is the transition latitude from where, again, angular momentum conservation is enforced and radiative convective equilibrium is enforced, and you have this continuity. And of course, this kind of unrealistic feature has been somewhat easily explained by just assuming that, of course, here we're neglecting completely the presence, for instance, of large-scale baroclinic eddies. These baroclinic eddies would weaken the zonal winds and would, of course, remove these unrealistic features. And here I am just listing here some other interesting features of the solution: the dependence on the pole to equator temperature gradient, the tropopause height, the rotation rate of the planet. And again, these are, of course, things that you cannot really test too much in our atmosphere, in the sense that, of course, we have the rotation rate that we have, but for instance, there is a tradition of performing simulations with idealized models where actually you can change this parameters and see how the predictions from the theory are in fact well verified. And so here the question is, what might be missing? Well, we didn't include any seasonal cycle. The follow-up paper was Linsen and Howe, 1988, that did consider the presence of a seasonal cycle. That is where you basically look at exactly the same model, making exactly the same assumptions, and just imposing a radiative convective equilibrium profile that now maximizes away from the equator to basically capture the shift in the maximum solar insolation from one season to the next. And the Linsen and Howe model of the Hadley cell predicts a large asymmetry between a winter cell that becomes much stronger and a summer cell that becomes much weaker. And Linsen and Howe really argued that this could explain the disagreement with the observations in terms of the Held and Howe model, because basically this nonlinear response to an insolation that varies with latitude, with the winter cell that becomes much stronger during the solstice season, would imply that when you take the annual average, this winter much stronger circulations would dominate. That is to say, you would have a rectification of the seasonal cycle. That is, the result, the solution that you get by imposing a seasonally reinforcing is not equal to the solution that you get when you force the model by the seasonally averaged forcing. But it turns out that in reality, we don't see any evidence of this square-like behavior implied by the Linsen and Howe model in the observations. Of course, we didn't include at all the influence of moisture, but one can show, and this is done in Hell 2000. These are a beautiful set of notes that Isaac Hell developed for a summer school in Tokyo, where basically you can show that what you expect moisture will do, again, just if you try to include moisture in the Held and Howe model. Of course, now you cannot solve for the model anymore, because of course now your heating depends on the moisture, which depends on the resulting flow. So of course you cannot really close the model and obtain analytical solutions, but you can show that in reality the influence of moisture will not affect the extent of the Hadley circulation. It will affect the strength of the Hadley cell, and in particular, as it always happens in an atmosphere where air goes up moist but comes down dry, you expect an asymmetry between the width of the ascending cell that you expect to be much stronger but also much narrower, and then a much weaker, gentler, more spread descent in the ascending branch of the Hadley cell. So you get this asymmetry between much stronger and latitudinally confined ascending motion and a much more spread out and gentle descending branch. And then, of course, and this is where a lot of work has been done recently, you can actually show that the baroclinic eddies develop in the extratropics and, of course, interact with the Hadley circulation. They force the angular momentum conserving winds to deviate, the zonal winds to deviate from angular momentum conservation. And you actually can show, and this is work done by Schneider through the years, Tabio Schneider and collaborators, you can show that the influence of the eddies, which force the Hadley cell to deviate from conservation of angular momentum, would not only weaken the zonal winds, but would actually strengthen the Hadley circulations. And importantly, the influence of the baroclinic eddies would force the scalings predicted by the Hadley by the Held and Howe theory not to be verified in our atmosphere, or at least in simulations where you account for these interaction between the tropics and the extratropics. And here, again, I don't know how I'm doing with time, but I just wanted to show you how what we see in the observations, and why there is reason to believe that the Held-and-Howe model doesn't necessarily apply throughout the seasonal cycle of the Hadley cell, and if it does, it only applies for the solstice seasons, especially for the southern cell, so for northern hemisphere summer. And so this is a plot that shows the observed Hadley circulations divided in season, DJF, so December, January, and February, March, April, May, June, July, August, September, October, and November. And these are the Hadley cells. You see that in your equinox seasons, the cells are more or less symmetric, not quite, about the equator. And the filled color contours represent, basically, it's the eddy momentum flux convergence of divergence. I don't want to go into the details, but basically represents one measure of how the baroclinic eddies that originate from the mid-latitudes that propagate into the tropics can influence the Hadley circulation. The one thing that I want you to pay attention to is this gray shading. This gray shading is a local Rossby number that basically measures how close or far the circulation is from conservation of angular momentum. So this filled contours will tell you this is the range of latitudes where the circulation does behave as angular momentum conserving, is approaching the predictions from the Held-and-Howe model. And notice how throughout most of the seasonal cycle, basically there is almost nowhere this prediction is well verified. That is to say, we cannot apply, we cannot expect, for instance, the strength or the extent of the Hadley cell to behave as predicted by that simple theory. But as I said, there is an exception. Now let's look at the, as we call it, the winter circulation. This is the winter cell in JJA, that is the southern cell that develops basically in the hemisphere corresponding to the winter, because it's, of course, the northern hemisphere that is experiencing summer in June, July, and August. Notice how there is this very large asymmetry between the southern cell that is much stronger and much broader than the very weak and narrow northern cell. And notice how for at least this season, June, July, and August, we see that in the upper branch of the Hadley cell, for most of the extent of the Hadley cell, angular momentum conservation, the cell is approaching much better conservation of angular momentum. So that is to say that we should not be, it is true that now it is well understood that the Hadley cell is strongly influenced by baroclinic eddies, and so the Held-and-Howe model does not necessarily apply to the observed Hadley cell, with the important exception of the winter cross-equatorial Hadley cell in northern hemisphere summer. And this connects me to the things that I'll be talking about, I don't remember when, but I think on Thursday on monsoons, because in fact now I think it is well, I think that there is consensus in the literature that large scale, at least large scale monsoonal circulations, and I'll try to make this connection more explicit next time, can really be interpreted as cross-equatorial Hadley circulation that approach, or at least start approaching, conservation of angular momentum. And here is a list of the references that I used, and I think I'm more or less on time, so I'll stop here and I'll take any questions.
Yeah, in the beginning you had mentioned that the precipitation maxima is in the northern hemisphere, and that is mostly because of the Atlantic, that south to north oceanic transport.
Yep.
So from that, can we conclude something like the contribution of Atlantic ITCZ or the Atlantic Hadley cell is more towards the global mean or something?
Yeah, so that's the big difference between the atmosphere and the ocean, right? The ocean have boundaries. What happened in a basin remains somewhat localized. But when we think about this global energy budgets, the atmosphere has no boundaries. And so what happens in the Atlantic in terms of the ocean circulation spread out through the atmosphere globally. And in fact that the ITCZ is north of the equator, you actually see it much more pronouncedly in the Pacific than you see it in the Atlantic. But that is because any perturbations is spread out by atmospheric circulations, and then it impacts much more the global behavior rather than the local behavior. Does that answer your question? And again, let me go back to this schematic that I had. So the fact that it's really again, because many hypotheses had been put forward to explain this northward shifted position of the ITCZ. One that might seem reasonable is the fact that maybe the northern hemisphere is warmer because there is more land masses. And in fact, in reality, it turns out if that were the only thing influencing the asymmetry in the top of atmosphere radiative budget, you would see that the northern hemisphere is losing more energy in the northern hemisphere, especially in desert regions. And in fact, if that were the only thing influencing this asymmetry, the ITCZ would be south of the equator, not north of the equator. And so basically, the fact that you need a northward shifted position of the ITCZ is because we see actually very little asymmetry in the top of atmosphere, radiative balance. Again, a little bit maybe that would suggest that it's the northern hemisphere that is losing slightly more energy than the southern hemisphere. The ocean is more than making up for that loss, and it's making the northern hemisphere with net energy input. And so now it's the atmosphere that needs to transport that energy back into the southern hemisphere. And because the Hadley cell, in general, not always, but the Hadley cell transports energy in the direction of the upper level flow, then you need to have an ITCZ that is north of the equator, an ascending branch that is north of the equator, so that the Hadley cell can transport energy from the north and to the southern hemisphere. The energy flux equator, exactly. And then again, when you start looking at regional seasonal variations, the co-location between the energy flux equator or the co-variation and the ITCZ is not necessarily one-to-one, but in general, yes, the energy flux equator is a proxy for the ITCZ position. Yeah, so of course, this requires, and again, maybe, well, I haven't really exactly thought completely about what I'm going to be talking on Thursday, I think, and so maybe if there is interest, we can talk a little bit about that. But basically, it turns out, so in this, right, in this framework, which applies to the global average, you basically are saying, and that is why you are so interested in the energy transport and metrics that can tell us something about the ITCZ based on the energy transport. You're basically saying you're taking a vertically integrated approach, you're writing an equation for the vertically integrated moist static energy or energy budget, and you're saying that your atmosphere needs to diverge energy from the regions in which you have net energy input, right? Yes. So net energy input being what comes from the top and what comes from the bottom. When you look at this perspective, the zonally averaged and annually averaged, then you're saying, okay, there must be an asymmetry in the net energy input that makes the northern hemisphere more favorable than the southern hemisphere. And so the top of atmosphere doesn't help you much. It's all about the surface fluxes. But then when you are looking at monsoon regions and you try to apply the same arguments, because now monsoon regions, at least to the extent we're interested in, of course, the ocean contributes, and that's where I think some of the things that you're saying refer to. But for instance, over land, the surface fluxes are constrained to be close to zero because your land has very little heat capacity. So that is to say that when you start applying these considerations to more regional effects and more seasonal effects, then there are other things that matter. But yes, absolutely. Part of it is also the fact that during monsoon seasons, you have these large shifts in the Hadley cell or the ascending branch.
Simona, thanks for a nice talk. I would love your comments on Plumb and Who and Kerry Emanuel's update on that.
Yes.
That's still kind of following the axisymmetry.
Absolutely. So there is, in fact, I don't have that. So just to address this question, there is this series of beautiful papers that all build theories of some aspects of the general circulation of the atmosphere, starting from the Hadley cell going to the monsoons that build on these axisymmetric ideas. And so the Held-and-Howe model is for a forcing that is the annually averaged forcing. Then the Lindzen and Howe expanded this theory to considerations of a seasonal cycle. You can think of the sea surface temperatures, that's how they interpret it, or the radiative equilibrium temperature that you would get with the seasonally varying forcing. And then Plum and Howe basically emphasized, and that is really the more direct applications to the monsoons, looked at what this theory would predict if now you have a forcing that is localized just in the subtropics. And what this means is that you don't have any gradients in the radiative convective equilibrium temperature across the equator, you just localize it. And you can show, and then I'll try to explain physically why you can get that threshold behavior in the subtropics. You can show that as you amplify, when you turn, you start from a weak forcing in the subtropics, and then you crank the forcing up, you see a transition from a very local and weak Hadley circulation to a much broader, larger, stronger, global cross-equatorial Hadley circulation that looks very much like the cross-equatorial circulations that you see in the summer over monsoon regions. And so basically this threshold behavior arises from the fact, this goes back to the definition of angular momentum and conservation of angular momentum. Conservation of angular momentum, one can show that the meridional gradient of angular momentum is proportional to the absolute vorticity, the sum of the planetary vorticity and the relative vorticity. Conservation of angular momentum means that in the upper branch of the Hadley cell or in the troposphere, you would have no meridional gradients of angular momentum. And so that corresponds to a condition that your absolute vorticity is equal to 0. When your forcing is close to the equator, F is small, and so you don't need much forcing to get a condition in which, again, the relative vorticity that is induced by your forcing is large enough to cancel the planetary vorticity. As you put the forcing in the subtropics, now the background planetary vorticity is not small. You're looking at an atmosphere in which rotation starts becoming important. Rotation gives a vertical stiffness, as we sometimes say, to the atmospheric column. So you need a larger forcing to get it going, a larger forcing to finally get a relative vorticity that is large enough to cancel the planetary vorticity. And they showed that, in fact, in their of course, in simulations are always a little bit different, numerical simulations from your theory, because there is always a little bit of numerical diffusion. But basically, they showed that when the forcing is weak, you get something that is just local. You still get a little bit of the returning, but it's nowhere near conservation of angular momentum. It's only when you kick the system hardly enough, you force hard enough, then you get this global overturning circulation that very much looks like a monsoonal circulation. And so their argument there was, maybe this is related to the rapid onset of the monsoon, the fact that you go from that the monsoon kicks in is, and in reality, let's say that applying this theories to the real atmosphere is a little bit difficult because, again, this is something that I didn't have time to really go into the details, but again, the RC is never a plausible state whenever you have non-zero gradients of your forcing across the equator. And in our atmosphere, there is always a non-zero forcing. And so that is to say that it's a bit hard to apply these reasonings to a circulation in which you already have a seasonal Hadley circulation that is forced by just the variations of seasonal insolation. And again, that is maybe something that I can, and the other thing, the Emmanuel, 1995, extended this constraint, and basically you can show there is a constraint on the gradient and the curvature of your forcing using basically this quasi-equilibrium. I don't know if quasi-equilibrium has been touched upon yet in this school. I'm sure it will, maybe, or maybe I can do it myself in my second lecture. We'll see how this develops, but basically they're just using some more modern ideas of how moist convection interacts and influences the large-scale circulation. Then you can basically translate that constrain on a constraint on the gradient and curvature of the moist static energy in the boundary layer, in the subcloud layer. So work that I did with Tapio Schneider when I was a student and a postdoc was based on aquaplanet models that try to put all of these ideas that were floating around, axisymmetric ideas, angular momentum conserving ideas, to consideration of the influences of the large-scale eddies on the Hadley cell that you see throughout the year. And basically, we showed that maybe, again, we're still really trying to understand all of the implications of these results that are based on IDLS models and observed monsoon, but this has been somewhat verified by work by other people as well. Maybe the transition that you see in monsoons is not necessarily a transition from an RC state to an angular momentum conserving circulation, but it is a transition from a circulation, a Hadley cell that is not angular momentum conserving, is strongly influenced by the eddies, to a circulation that, as we saw, for instance, for the observed Hadley cell in JJA, does transition to conservation of angular momentum. And there is this interaction between the winds that you get in the upper level when you have a cross-equatorial circulation and the Hadley cells, because once you start having a standing branch that is shifted significantly off the equator, your angular momentum conserving winds are no longer zero at the equator, you develop easterlies. And so as you start developing easterlies, these large-scale eddies that come from the mid-latitudes are very much like Rossby waves that propagate in regions of upper-level westerlies. And once you start having easterly flow, basically, there is the Hadley cell itself kind of shields itself from the influence of the eddies and can start approaching angular momentum conservation. So thank you for this remark. Yes.
Nice presentation, ma'am. Here you mentioned two theories, held theory and held and how. Like in the held theory, you like radiative convective equilibrium is zonal gradient with presence of the zonal winds with presence of the meridional gradient. And another theory shows that the meridional changes along with the there is longitudinal variations.
I'm not, can you repeat
Yeah, zonal winds of the angular momentum is conserved in the held and how theory. Yep. That indicates the meridional changes only. Meridional variations.
Meridional variations of?
Like winds, moisture, or like here we are constant in the longitudes only. We are considered as the latitude versus pressure levels.
Yeah, so the theory doesn't account at all for variations with longitude, if that's what you're asking.
Yeah, but here I am asking about regional Hadley cell is also there. Regional changes of the Hadley cell.
Regional changes of the Hadley
Hadley cell, which is good for regional changes of Hadley cell, along with the like tropical region.
Practical reason?
Tropical region.
Tropical region.
Yeah.
So maybe let's see if I understood your question. You're trying to say, how do we go from a theory that is applies for the global average, where we can neglect any zonal variations, yes, and how can we apply that to regional Hadley circulations and regional monsoons? Yes, is that what you're asking? Absolutely. This is a very good question. In fact, this is a question that I mean, this is really a great point in the sense that in many ways, the globally averaged Hadley cell is somewhat a construct, in the sense if you're looking at what happens ocean basins by ocean basins, monsoon region by monsoon region, you never actually see the globally averaged Hadley cell. There is a regional expression. Absolutely. One of the advantages, of course, of using this zonally averaged framework, and now there is a lot of work that is trying to extend all of the theories that have been developed based on zonal averages, global zonal averages, to regional considerations. So again, one of the advantages is the fact that, of course, your budgets simplify tremendously. So think about the angular momentum budget. As you say, we only need to worry about the the meridional direction. You don't worry about the zonal fluxes of angular momentum. Same thing when you think about the energy budget, you are just think about the meridional distribution. Yeah, absolutely, I agree with that. So we looked a little bit with one of my former students at Caltech at the angular momentum budget and the energy budget over the Indian monsoon region. And we actually found that at least, of course, this is where you need to take domains that are large enough, but you can do it over the Indian monsoon region. There are domains over which what comes in the zonal direction is more or less equal to what goes out. And that is to say that even if, of course, in reality, all of the balances are two-dimensional if you vertically integrate or three-dimensional if you don't vertically integrate, in reality, very much reduce to what you see when you consider the global averages. But of course, you're totally right in the sense that it's not at all straightforward to apply theories for the global zonal average to regional cases, and that is where a lot of work is being done. There is work that is being done both in terms of extending some of these energetic ideas to, again, considerations of not only the meridional divergence, but also the zonal divergence. There is also now a lot of work that is trying to identify a regional Hadley cell. So looking at the divergent component of the circulation in both, not just the meridional, but also the zonal direction. But again, this is very much still ongoing.
In a way, it's kind of, how do you say, when you do the decomposition between the stationary and transient edges?
I would say that it depends a little bit on what you mean by stationary eddies, right? In the sense that if you're looking at the global mean, the stationary eddies are very important in the northern hemisphere, but they are the monsoons themselves. Because the monsoons are stationary eddies at the end, right, or quasi-stationary eddies. So there is a little bit of debate in the literature. And so, for instance, Tiffany Shaw had a very nice paper in 2014 where she looked at the transition in the angular momentum budget in the solstice season in June, July, and August, and she sees this amazing growth and therefore contribution to the global zonal momentum budget. She looked at the global zonal average by the stationary eddies. But of course, that is the Indian monsoon itself. So when instead you're interested in looking at what happens over the Indian monsoon region, and if now you define the stationary eddies not as the deviations from the global zonal mean, but the deviation from your sector mean, then you don't have any stationary eddy because the monsoon itself is. So I think, again, this is to say that there is still some disagreement as to exactly what you are talking about, in the sense that the stationary eddies are very important, both in wintertime and in summertime. In summertime, in the tropics, the stationary eddies are primarily monsoons.
Any other questions? If not, maybe let's thank.
Maybe there is one final question here.
This can vary, like the Hardy cell. For example, in the monsoon region, we see this intra-seasonal northward movement on 10 to 28 time scale. Also, we see this northward movement of the this convective cell. So, like, have you done anything on those lines, like how that can impact, like how that fits into this sort of framework?
So I didn't quite I think that you're saying that, of course, we don't just worry about variations from the zonal mean, but also variations from long time mean. There are seasonal variations. Yes, we've looked a little bit at that, both from the perspective of, primarily from the perspective of the energy budget. And of course, when you're looking at seasonal transitions, some of the terms that you usually neglect, such as, for instance, time variations, the storage terms are not necessarily negligible anymore. Yeah, so as always, we start from the zonally average, long-term average, because the budget is very simple. You can safely assume that there is no storage. Yeah, so you have these very simple arguments. When you start looking at seasonal variations, so for instance, that's where I said, for instance, again, here I'm talking about the energy budget. I I said how, in general, the Hadley cell is energetically direct. In general, in reality, it's not always like this. Energetically direct means that it transports energy in the direction of the upper level flow. We see this in observations. We see this, for instance, over the Eastern Pacific Ocean. You see it quite well. Even in regions where you would call, deep convective regions, where you have a lot of precipitation, you can have situations where, in fact, vertical profiles of the vertical velocity are much more bottom heavy than top heavy. And if you look at the resulting overturning, you get that instead of having this first baroclinic mode picture where you have a deep ascent, and again, the Hadley lower and upper branches, Hadley cells being confined to thin layers close to the surface and the top of the tropopause, you actually see that you can develop shallow return flows. What this means that instead, again, of having a deep circulation that is in which the divergent motion away from the ascending branch is close to the tropopause, it's much closer to the lower to mid troposphere. And so now, if you think about this profile of moist static energy, now, in fact, the moist static energy transported by this return divergent flow is lower. This value of the moist static energy is lower than the value at the surface. And so you can have situations where, in fact, the Hadley cell is importing energy and its ascending branch rather than exporting energy of this ascending branch. And so this is to say that then some of, again, the arguments associated with these energetic metrics don't work anymore in trying, for instance, to explain position of the ITCZ seasonal.
Hello. So you just mentioned about this bottom-heavy Hadley circulation where energy is transported. So basically, energy is imported instead of being exported. So what physical processes can drive such shallow flows? Like, is there any surface fluxes or changes in surface fluxes or anything which would result in such shallow flows?
Yeah, so what we, and again, there is a lot of, let's put it this way, that there is a lot of work looking, for instance, at what happens over the Eastern Pacific from the perspective of just convection. We did some work looking at what that implies for the structure of the Hadley circulation. And so what it turns out is, in general, what we find, and that is also a little bit consistent with some theories that are less thermodynamically focused and more dynamically focused on where the ITCZ is, we tend to see that, again, the shallow return flows tend to occur in regions where sea surface temperatures tend to be smaller, but the curvature is strong. And so it seems that there, the flow is strongly constrained by your lower level convergence. And so it remains, the vertical motions remain much more bottom heavy rather than top heavy.
So would that mean that these flows are mostly observed over land, like there is a land ocean, sorry, over oceans? That means that there would be a land-ocean contrast.
We've looked at this primarily over the ocean.
Okay.
Yeah,
okay.
Especially in the asymmetry between the Eastern and the Western Pacific.
Okay.
Yeah, and so that is to say, right, there are different, apart from this global zonally averaged view of convection, right, or how it is embedded within the ascending branches of the Hadley cell, there is a little bit of history of theories for where the ITCZ is located. And for instance, going back to Linzen and Negam, for decades, the prevailing view was that of convection being primarily driven by boundary layer dynamics, and where basically the lower level convergence maximizes, and that brings up the role of the sea surface temperature distribution. And then theories have shifted a little bit away from this dynamical theories, much more on energetics or thermodynamics theory that are much more agnostic about where the boundary layer forces lower level convergence, in the sense that we know that convection is associated with convergence, but it's not necessarily driven by convergence. What another view, again, emphasizes how it's much more thermodynamically driven, so where you have instability. And so, again, follow-up theories have focused much more, for instance, where moist static energy maximizes. And so you're a bit more agnostic as to, again, well, you know that the convergence will adjust, but you don't necessarily view the convergence as driving the convergence. That said, it is clear that both in simulations and in observations, we do see that there are some regimes where it seems that convection is more strongly dominated by the resulting dynamics, and other regimes, especially when you have high sea surface temperatures, where it's more controlled by thermodynamics.
Well, let's thank Simona for a nice talk.
Thank you.